I'm going to go through the questions on page 67. I'll go through them in two stages. The first part I'll do really quickly because it's the same as page 64. So if you see any part of this that you don't understand, have a look back at the video for the question on page 64. So we've got a sequence of lights that change here. The red stays off and then goes on for a while. The amber goes on and off. The green goes on and then stays off for a while. We get asked some fairly simple questions to begin with. So how many output displays are required? Now you can see that we've got an output of a red going on and off, an amber going on and off, and green going on and off. So the output displays are 3. I need 3 different output displays. How many different patterns are required? Well, you can see I've got 1 pattern here, 2, 3, 4 patterns. So 4 patterns are required. How many inputs are required to cover this number of combinations? Well, for 4 outputs, it's 2 inputs. Again, you can look at the last video for that, and that gives you some information on how to work that out. Next, we're going to complete a truth table. So what we're going to do is, down here, we're going to write what happens to the red light, what happens to the amber and the green. Now I can see if I look at the red, it's off, off, and then goes on and on. So down here on the table, it's off, off, on and on. Amber up here goes off, on. So 0, 1, 0, 1. And green is on and then off for 3. So I'm going to look at the next questions, which are asking me to complete a Boolean expression for the red light, amber light and green light. Now if I look, red light is a bit of a weird output. It's 0, 0, 1, 1, and I know that from knowing my kind of logic tables, I know that that isn't an output from a specific logic gate, but it gives me a clue here in the question. Is it the same or inverse of an input? So what I can see is that actually it's exactly the same as B. So there is no logic gate in here. It's just that red equals B. Now if it had been the opposite way around, say red had been on, off, off here, that would have been not B, and in Boolean expression I would have put a bar across the top here. Next one up, I've got amber, so I need to work out what the amber does, and it goes 0, 1, 0, 1. Same thing, I know that that's not a logic, an output from a single logic gate, so I could combine logic gates together, but same thing, I'm looking over here and it's exactly the same as the input from A. So I can put that amber just equals A. There's no logic there at all, no logic gates needed. It's just a direct copy. So red is doing whatever the B input does, and amber is doing whatever the A input does. Now we get down to green, and green goes 1, 0, 0, 0. Now I've kind of learnt my logic gate and all their output, and I know that that is a NOR gate. So I know it's a not OR gate. Now you can kind of work it out. If you look, it's only on when both of the inputs are off. When either input A or input B or input A and B are on, then it's off. That means it's the opposite to an OR gate. So it's a not OR gate. So I can put down here that green equals B nor A. Now in Boolean notation, that means that it's B or A not. So it's a weird way around to do it, but it's B or A and then it's not that. So that is a NOR gate there for B and A. Now I've rushed through all that a little bit because we've done that before on the last video for page 64. So if you're not sure about any of that, or I haven't explained it very well, have a look at the last video. Okay, so we've done the theory of this circuit. We've worked out the Boolean expression, we've worked out a truth table. Now we need to make it practical. We need to come up with a circuit that will work with different logic gates. So what I'm going to do is I'm going to start really simply by thinking about what inputs and outputs I've got. I know if I look at my table here, I've got 2 inputs, A and B, and I've got 3 inputs, red, amber and green. So that's the first place for me to start. So I'm going to here, I've got input B, I'll put it in the circle, and I've got input A. So they're my 2 inputs. I've also, output wise, I have got a red light, I've got an amber light, and I've got a green light. Oh, here, like that, okay? Now, this is where this bit here is really useful to me, because I've worked out what they all do. So I know that the red output here is just whatever the B input is. So I could just connect that to there. So, like that. A, or amber, is connected directly to A. So to get the amber output correct, I'm just going to connect it directly to A, like that. Okay, I'm trying to keep straight lines. I know I'm drawing it roughly, but try and keep straight lines rather than using diagonals, because that's how you normally do a circuit diagram. Okay, next thing, green. This one's a bit more complicated. Now, green is B nor A. So I'm going to draw my NOR gate in. So it's an OR gate, which is that shape there. And then I put a circle on the end of it to make it a NOR gate. And I know that a NOR gate goes into green. It is B nor A, so I need B and A to be connected to this NOR gate. So from here, one input to the NOR gate goes up here. I'll put a dot on it to show it's connected. In circuit diagrams, when lines cross over like that, they are not connected. Okay, it used to be that people put like little bridges on, but these days in a circuit diagram, when they cross over each other, they're not connected. They're only connected when you put a dot on. Okay, I need to connect this NOR gate to A as well. So I'm going to connect it up there to A. Now that circuit diagram now does everything that this table does. It completes all these Boolean expressions here, and it makes your circuit do this. Okay, so the next bit that we need to do is we need to add a counter to the system to make it work automatically. We could have kind of some switches here and press them to get the outputs that we want, but we want it to work automatically. So what we're going to do is we're going to use the counter integrated circuit that we've been looking at, and this is the circuit that we're going to use. So it's got 4 outputs, it's got a clock input, and it's got a reset button. Now we know that we only need 2 inputs, so from our circuit we're only going to need to use the first 2 outputs here from our counter integrated circuit. So we're only going to use A and B. C and D at the moment aren't needed. So it's going to be a little bit messy, but I'm going to add this circuit to my logic circuit. So down here I'm going to add my counter integrated circuit. I'm going to draw it really quickly. So I know I've got 4 outputs here. I know here I've got a clock input, so we indicate that by that, and here I've got a reset button. Now I just want to do, so I've got D, C, B and A as outputs, and I only need 2 of the outputs. So I can very quickly just link A up to there and B up to here. Now in an exam they'd want you to do this a bit more neatly, maybe practice it first and then put it down kind of neatly. So you could practice it in the margin and then put it down neatly on your exam question. But there's nothing wrong with this if your lines all match up. Now for the input here I need a clock input, and generally this could come from a 555 timer or something. So generally we just put a square down here and say the clock input comes in here. I've got my output B and my output A there. Now, as a reminder, and just to make this a bit more kind of easy to understand, hopefully, the integrated circuit here is a counter. It's a binary counter. So it's got 4 outputs, DC, B and A. Now we're only using B and A. And if you remember, the counter sequence that we always have with 2 inputs is 0, 0, and it's 0, 1, 1, 0, 1, 1. And we can see that this is actually counting up numbers in binary. So if you look here, this would be binary 1 or 0, this would be binary 2, this would be binary 4, and this would be binary 8. So if I look down here, 0, so there's no 1s and no 2s, so that would equal 0. Next I've got 1, 1 and no 2s, so that would equal 1. Next up I've got no 1s, but I've got 1, 2, so that equals 2. And then lastly here I've got 1, 1 and 1, 2, so that would equal 3. The thing with this is, though, that our counter has got 4 outputs, so it's going to carry on going. What are D and C doing? At the moment, they're 0, they're not doing anything at this point. They're not giving anything out at all, they're staying at 0. But once we get to this point here, then they start producing an output. So the next thing up was I would need binary 4, and binary 4 would be 0, 0, 1 there. So all of a sudden the C output is doing something. Then it would be binary 5. I need binary 5. So the C output again is staying on, and this would continue down until we'd filled all those up. So I would have an 8, a 4, a 2 and a 1. So I can go right up to kind of 15. So it carries on, and we don't need to know this, but you can see from this that if I actually attach this counter to this system, what would happen is it would run through the sequence, then it would carry on running for a long time, so almost twice as long. It'd go through all the other numbers that it would, and then it would stop, and it wouldn't restart. So I need to get a reset on there. Now, if you, in an exam situation or in a practical situation, if you made this circuit, it would work fine, and it would run through the sequence once. But I want it to run through again, and I want it to keep running through it. So I need to reset it. At some point, I need it to reset. So I need to put a signal into the reset when it has run through the whole sequence once. So I want it to do this. I want it to do that. I want it to do this one. I want it to do this one. I want it to do this one. But I don't want it to go any further than that. And I can see that at this point, this output suddenly starts working, or rather an input to our circuit, but it's an output from the integrated circuit. And that hasn't happened before. So I could use this here from output C as an indication of when I want the whole system to reset and start working. So if I joined C to the reset, it means it would allow this whole circuit to work. B and A would do their things down here until they got to this point here, and then when C kicked in and the counter at C pushed out an output at C, it would reset the system. The whole system would then reset, so it'd go all the way back to the beginning, and it'd do this again, and it'd keep doing that. And that's a way that we can use an integrated circuit counter to control a logic system and get it to work through a sequence and keep working through the sequence. Now, that's quite a complicated thing to understand. If you don't understand it, please contact me. I will keep going through these the questions that I get from pupils, and I'll keep making new videos to try and explain them.